So I want to give you an example with a manometer. We're going to be using manometers a lot. And in this example, we're measuring the pressure difference between a hallway and a master bedroom. So in the hallway here, we see, I'll actually kind of teach you how to read this manometer. So the way that the manometer works is it measures right here, this opening, right? So it's measuring that port. And then it's measuring, of course, this port. But this port has a tube on it, so it's actually really measuring this room right here. So we can measure in this room, and then we can measure in reference to this room. This is what's really important about this. We're measuring references. It's always in reference to something. So I don't just go in a room and say, this room is -2 pascals. -2 pascals in relation to what? In relation to the master bedroom next door, in relation to this closet, in relation to the attic, in relation to outside. What is it in relation to? Because these aren't what we call absolute values. I'm not just going in there and measuring the atmospheric pressure. It's always in reference to some other place. So in this situation, we're measuring the input here. So we're reading in this is how I like to remember it, input. In the hallway, it's -2 pascals in reference to, REF, in reference to the master bedroom. So in the hallway is -2 pascals in reference to the master bedroom. So in other words, the hallway has less pressure than the master bedroom, -2 pascals less. Well, pressure goes from high to low. So which way would the air be moving? It would be moving from the master bedroom into the hallway, right? It's going from high to low because in the hallway, it's -2 less. All right, so is this a problem? Mold growth in the master bedroom, right? Now we have mold growing in the master bedroom. Is that affecting the hallway? Well, our manometer says it is. If there are spores flying around in the master bedroom, they're going into other parts of the home. And see, already we're starting to see why this is important. Now, as an indoor environmental investigation, I would look at this master bedroom and say, yeah, we'll take air samples in here. We'll document the problem in here. We got to clean this room. There's mold growing in this room. But because I understand building science and I understand building pressure, I can actually measure what the risk is for the mold transferring into the hallway. So that's one example. Now I'm going to confuse you and switch the actual, I'm going to switch this over to the other side. So now we're looking at the containment zone. The containment zone, in the containment zone, it's -5 pascals. So let's pretend that they sealed this area up. They're ready for remediation. There's plastic separating this room with the rest of the house. So in this area, it's -5 pascals in relationship to the hallway and living room. Is that a good thing or is it a bad thing? It's a good thing because they're protecting the hallway from the mold that they're remediating. And if they're ripping out drywall and ripping off ceilings and stuff is flying all over the place, you don't want that to fly into the other area of the house. So if it's under -5, what that means is this area, I'll get my arrow, this area is coming in, this air is coming in and trying to get into the containment zone, which is what you want. You don't want it the other way around. So manipulating air pressure for mold, understanding air pressure for mold inspection even, very important. Now, let's take a look at something like this. We're dealing with, there we go. We're dealing with lots of pollutants outside, lots of pollutants. So now just imagine that you have your manometer and you're measuring the pressure difference between inside the entire home and outdoors. So maybe the house is -10 pascals in relationship to outdoors. Well, what do we have to worry about outdoors? Well, we have a lot of pollutants from cars, which, you know, most of them are what we call PM 2.5, very small particles, less than 2.5 microns. Industrial stuff, you're dealing with heat and humidity from these types of things. You're dealing with pollen, you're dealing with people doing pesticides, wildfires, all these things that are making their way into the house because it's negatively pressurized. Now, why is it negatively pressurized? Well, that's something that you can start learning, doing your building science inspections and figuring out for customers. But if we have a building that's built tight, then we don't have to worry about these things as much because we're controlling how the fresh air is coming in, right? The name of the game is to seal this building up as best as possible and then control the air with usually mechanical ventilation coming in that's going through a filter that's going through an air conditioner and being conditioned, that's being dried, or whatever the case may be. Here's an interesting video I wanted to add here. Look at this humidity, right? So we got about 56% humidity in this house. Look what's happening behind this thermostat right here, right? Mold growth. Mold is growing in such an interesting pattern. You see how it's kind of growing in these spikes? That is a telltale sign that they're dealing with a pressure imbalance in the house. There's less pressure inside than there is outside, for whatever reason, at least in this area. That means it's pulling air from outside, and this is a hot, humid climate. This is a Florida home that we're dealing with. So there's hot, humid air going down the wall, coming out of this penetration behind the thermostat, and as soon as it smacks into this 70-degree wall, 73-degree wall, whatever it is here, it's sweating. It's going to sweat as soon as it smacks into that drywall, and if this is a continual thing, you're going to see mold growth. I want you to see what happens with my, my hygrometer here. So it's 56% humidity. I'm going to hover it over the thermostat, and look what happens to the humidity. 67%, 70%, 71%. So you can see that the humidity is steadily increasing, 76%. So we obviously have some air infiltration happening here, and it could be a lot of penetrations that this is happening to behind every outlet, every light switch, because of a pressure imbalance in the house. Here's some issues that you might see. Take a look at this recessed light. Again, the spikies. These little spikies are a telltale sign that you're dealing with a pressure imbalance, right? Hot, humid air getting sucked in. This one right here, it's interesting. Mold growth happening. Right here on the actual drywall. Had multiple roofers come out. We can't find the roof leak. We can't find the roof leak. It was not a roof leak. Look at where it's coming from. You can actually see right here, there's air getting sucked out, and how can you see that? You can see mold, an airstream coming out just like this, and then it hits the vaulted ceiling. And so there's an air pressure imbalance here, sucking air out and smacking into the drywall, causing condensation. And you go up there with your moisture meter and it shows that the moisture levels are high. I told you there was a roof leak. Well, no, it's high because it's condensing right there. It's a condensing surface. Here's another issue that we find, mold growth behind outlets. That means heat and humidity is coming in from an exterior space. This is what it looks like behind from the attic side. Completely open penetrations right here, right? So these are just fundamental things that I want you guys to understand. Now, this is all hot, humid climate stuff I'm showing you right here, but the same is true in the wintertime. Think about if in this situation, right, in the wintertime, let's say this is 15-degree air coming in, Fahrenheit. Well, the dew point in the house is probably, it's probably reaching dew point in the house. So when the actual warm air in the house smacks into this 15-degree drywall because 15-degree air is coming in, you're also going to get sweating. So this is no different, right? It's just the mechanics are different, but the fundamentals are the same. Check this out. You see a little bit of mold growth starting to happen right here on the pocket door. And why is that? Well, it's because there's a pressure imbalance pulling in air from the pocket door. Check this out. Look at all these things in this room. You got pesticides and paints and lots of pollutants, and then you have an air handler. And I'm just trying to show you some examples of why this stuff is important, why these pressure imbalances are important. So this mechanical system is actually pulling air in from the garage. And so here you have these pollutants in the garage potentially getting sucked in. I should say potentially. I actually ran some tests in this house, and the gasoline levels were high. And so just basic things like that are really, really important to watch out for. This middle one is really interesting. So check this out. What happened here was there was some mold growing right here. And they couldn't figure out why. They're like, why does mold keep growing? Get up in the attic. You look down. No ductwork passing by sweating. No roof leaks. Why is there mold growing right here? Well, once you actually understand air pressure, it becomes quite simple. What is this? This is a return. What does that mean? That means it's pulling air. There's a force here that's pulling air. So this hallway is likely under some level of negative, right? Assuming that they don't have the right amount of supplies in this area, which they didn't, then This room is in some sort of negative. So what's happening? This house had one of those old attic fans, like the whole home ventilators that they never sealed up. And check this out. That return is sucking air out of the attic. And guess where it's going? Oh, look at the direction it's following. Right here where the mold growth was. Right on the ceiling where the mold growth was. Why? Because that hot, humid air is passing across that cold drywall and causing condensation as it goes into the return. What about this one? All right, so we have a room where there were nothing but supply vents in this room, a lot of them. It's a big area, nothing but supply vents. And the return was in here, in this room. What does that mean? That means you're adding air into that room. You're adding and adding and adding. And then in this area of the house, the central area of the house, you're pulling. So you're pulling more air than you're getting back in the central area, and you're adding air into what was the master suite. What do you think is going to happen? Well, you're going to have pressure imbalances, right? So take a look at this. It's with a smoke pen. Look at that pressure imbalance. What do you think that's going to do with circulation, comfort, particulates, whatever, you name it? So this room is obviously under positive, right? Because it's actually, you're seeing the air getting pulled into the central area. But since that air isn't getting to the central area easily, that means that the central area of the house is under a negative. And we'll talk about that a little bit later. Here I am with a particle counter, right? I want you to see what happens with particulate levels as air infiltrates from the attic. So here I am, I'm checking a supply vent, a supply duct, just to show as an example that the particulates increasing were not coming from the ducts, not coming from the air handler. So take a look at these particle levels. They're going to be increasing slowly, right? They're increasing barely, but watch what happens when I put it at this crack right here. They start jumping dramatically because you have air infiltration that's getting pulled in from the attic as the air handler runs. So what are some other causes of pressurization? Mostly what we talked about here were mechanical systems, right? Mechanical system issues where return and supply areas are wrong and things like that. Stack effect is a big one. Now, this is something that's more common up north, especially in the wintertime, where the hot air rises. You know, hot air is less dense. Cold air is more dense. So since it's less dense, it rises. And when that air rises, well, the air is going up, right? So there's less air down here now. So air comes in to replace it. And so what's going to happen is you're going to have the air rising and going out, and at the bottom, air wanting to come in. What does that do? That means that the top of the house or the building is going to be under a positive pressure as air is coming out. And then the bottom of the house is going to be under a negative pressure. Why is that important? Well, what if the bottom of your house was a basement? Do you want radon coming in? Do you want moisture and other soil gases coming in and pesticides coming in? What if this is a building, right? And we're talking about energy efficiency. Look at all this heat escaping in the wintertime at the top. There's lots of reasons that we look for problems like this, but this is one of those other causes of pressurization. Here's some other things. We have here duct leakage. Duct leakage is a big one that causes pressure imbalances. So let's say I have my beautiful house here, right? I have an air conditioner. Wow, that's a horrible air conditioner. Let me make my air conditioner green. That's my air conditioner. And then I have a return here. Here's my grill. And my return's just sucking air. La 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 la. Right? And then because we're so smart in Florida, we decide we're going to run our ductwork in the attic. So it's going to go like this. Now this is horrible, right? Because we got one supply vent. But what do you think happens if this ductwork in the attic, like an attic, in the attic is leaking, right? There's air leaking out of here. Well, we just learned, right? If you have 1,000 CFM, for example, going into the return, 1,000 coming out of the supply, which is what should happen, right? 1,000 going in a perfect world, 1,000 is going to come back out. Pressure will be balanced, right? No harm, no foul. But What happens if you have all this duct leakage in the attic and now only 700 CFM is coming back out? What do you think is going to happen to the house? Well, you're still sucking 1,000 out of the house, but you're only getting 700 back because you're getting a lot of duct leakage into the attic space, which is outside of the envelope, assuming it's a vented attic. Well, now you're going to have 300 CFM coming in from unwanted spaces. So duct leakage is a big part of pressure imbalances and the reason for pressure imbalances. HVAC design, return and supply location is really important. Exhaust fans, we talked about exhaust fans. Range hoods is a huge one, right? If you're clicking on your range hood and it's 1,000 CFM range hood, do you have any makeup air for that? Are you controlling where the air is coming back, or are you just allowing it to come from the attic or wherever? Dryers, click on a dryer. That air is exhausting out somewhere, right, with the lint. It's not creating it. It's got to pull it from the laundry room or wherever it is. So that area could be under a local negative pressure, especially if a door is closed or something. And then you have wind. Wind is a very big one, especially here in Florida, because we have these houses that are sitting on the beach and there's a lot of wind-driven pressure, especially these condos that are like so close together, these big apartments that are so close together, and the wind tries to squeeze through and it pushes the wind pressure against the buildings. All of these things are some common causes, but just keep in mind that when we're looking for air infiltration in a house, that it's great to do the blower door test and to run these things, but you got to understand air pressure, and you got to understand why it's important. And once you start getting into that next level, other than just going in there and doing, the blower door test, understanding why you would even have pressure imbalances that would utilize those penetration points is the next level. It's really, really important.